All right, team, we're going to do a little review session here for the exam that will open up on Thursday. I've selected some problems from 5.4, 6.1, 6.2, and some from 7.2, since 7.1 kind of feeds into 7.2. And just last week, I posted a problem session for 8.1 through 8.2, which should suffice as review for those two sections. So let's get started. We're looking at section 5.4. This is the section on conditional probability. I'm pulling these problems from the back of the book, so you can refer to the book to get all the verbiage and the wording. Sometimes I distill it down so that I don't have to write as much, right? So number 12 says a single card is drawn from a 52 card deck. Okay, that's the experiment. Part A, we're asked, what is the probability that we will draw a king? What is the probability of drawing a king? Okay, we know how to do this. There are what? 4 kings in the deck and 52 cards total. So that gives us 1 out of 13. Easy, easy. Okay. Probability of drawing a king given we know we have a heart card. All right. So how many hearts are there in a deck? There are 13 hearts in the deck. How many kings out of those hearts? 1. Part C asks, are the events drawing a king and drawing a heart independent? Okay, so remember the symbol means independent. Are the two independent? Well, if they're independent, then we know that the following probability statement should be true. So the probability of drawing a king given you have a heart should be equivalent to the probability of drawing a king. So that's the question. Are these two probabilities equivalent? Well, we computed the two up here. This was 113. This is 113. Those are equal. That's a check. Therefore, this is a true statement. King is independent from heart. So that's one way of verifying independence using conditional probability. All right, let's look at another problem. This is problem 17 from the back of the book. Here we're given a table of frequencies. This came from a survey where they asked people whether they were more or less likely, or neither more nor less likely to buy a product if it was made in America, or if at least it had the saying "Made in America" on it. Okay, and they broke down the survey group into ages 18-34, 35-44, 45-54, 55 plus. All right, so there's our frequency table. Now we're going to use it to compute some probabilities. So the first thing it wants is us to compute part A, the probability that an individual is 35-44 given they are more likely. All right. So the way to think about this is when we have a given or a condition, it's sort of like we're pre-sorting the survey group according to the condition. So essentially, we've taken all of these people and we've sorted them so that all the people that answered more likely in the survey, all of them are in a room together. We're then going to walk into that room and we're going to select someone at random and ask their age. And we're interested in what's the likelihood that when we select that person at random, their age will be 35-44. Okay, so within the room that we're selecting from are all the more likelies. How many more likelies are there? There's 1,329 more likelies. Of the more likelies, how many of them are 35-44? 329. All right. Then, of course, We should punch it into a calculator to see what we get. Get something numerical. So this is approximately 0.25. So a quarter. So remember, when there's a condition, that condition tells you when you're reading the table to limit yourself to the row or column from which that condition comes from, right? So once they conditioned on more likely, I knew I was only going to use numbers in the more likely row. Whatever the condition is, if it's 35 to 44, then we'll only use numbers from that column. Here it was more likely, so we only use numbers from the more likely column. The total is always what goes in the denominator. And then you have to select the correct one for the problem, for the numerator. Okay, so now we're asked, what's the likelihood of walking into the room where we've sorted everyone according to age and all the 35 to 44s are in that room? We grab someone at random and ask them what their answer to the survey was. And our question is, what's the probability that their answer was more likely? All right, so how many 35 to 44s are there? The grand total there was 536. So we're now just in this column. How many more likelies were there? 329. Punch it into a calculator to get a little bit more numeric result so we can get a sense of how much it is. It's 0.61. See if I can get this. All right, moving right along. Now we're going to compute the probability that within the room with all the 18 to 34-year-olds, we grab someone who's more likely. So 18 to 34, the grand total there is 542. And the number of more likelies there is 238. Punch it into a calculator. And that's roughly 0.44. Okay. So I should say that in this last part, this part C, the question is asked in a sort of weird way. So it says something like, compare the probability that an 18 to 34-year-old is more likely to buy a product versus just any given individual. So we're conditioning on 18 to 34 to compare it to just the general population. So out of everyone who answered more likely, the probability of answering more likely now, since this is a simple probability, we go to the grand total, 2160, and then the grand total for the more likelies is 1329. You punch that into a calculator. 1329 divided by 2160. And that's roughly 0.62. So we can see that in general, a general individual is more there's a higher probability that a general individual is more likely to buy a made in America product than if we just pre-select for the 18 to 34-year-olds. So this one is bigger. Read the problem to see how this last part is worded, and because I just broke it down into what were the probabilities that we need to compute to answer the problem, but the wording is a little weird. So I would read over that problem, which was problem 17 from 5.4. All right, moving right along. Oops. Okay, so I'm gonna do a couple problems from 6.1 now. This is the section on discrete probability distributions. Here in problem 18, we've been given the distribution and the random variable X, big X, counts the number of marriages that an individual has been a part of. So how many times has an individual been married? Up to 5 times, which is crazy. If you've gotten married 5 times, you've got either got a problem or some bad luck. All right, so the context really doesn't matter. We can just answer these problems as we need to. Once we have a probability distribution, first thing we want to do is verify its probability distribution. So this is something that a number of you got hurt on either, I think it was the last exam. You didn't verify both properties. So remember, there's 2 properties. One property is that all of the probabilities are bounded between 0 and 1. Okay, so that must be true. All the probabilities must be bounded between 0 and 1. The second property then says the sum of all the probabilities should equal 1. Here you just want to, if you were doing this on a test, you would write it out explicitly. 0.272 plus 0.575 plus 0.121 plus 0.027 plus 0.004 plus 0.001. What does that equal? So you can't just do it in your calculator and say, there, I did it. Didn't you see me do it? No, I didn't see you do it. You didn't write it down. So write it down. Should be 1. Voila, a perfect 1. So both conditions have been verified. All right. Once we have verified we have a probability distribution, let's do a few things with it. First, we want to compute the mean. Computing the mean means computing the expectation of x. This is equivalent to computing the mean, which remember is the sum of the values times their probabilities. So that's 0 times 0.272 plus 1 times 0.575 plus 2 times 0.121 plus 3 times 0.0027 plus 4 times 0.004 plus 5 times 0.001. So that's how we compute our expectation, which is the same as computing the mean. Trying to make room here. There we go. So we'll punch that into the calculator. So the first term is 0, so I'm not even going to bother. And it's 1 times 0.575 plus 2 times 0.121 plus 3 times 0.027 plus 4 times 0.004 times plus 5 times 0.001. Oops, make sure you got all the zeros there. And so we get an expectation of 0.919. So this is our mean. Okay. Now they want us to compute the standard deviation. We've got 2 ways of doing this. I think one way is preferable when you have a probability distribution. It's easy to then add another column, either to the left or right, doesn't matter. This is sort of tough because I've got this x here. So this is not a part of the table. In this column, I will have x squared. So I'll take all the values here and I'll square them. I won't change the probabilities. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Okay, so these numbers are for x squared, and they go with the same probabilities as the x. So 4 goes with 0.21, just as 2 goes with 0.121. All right, so remember that the cool way to compute the standard deviation is to find the expectation of x squared and subtract the expectation of x quantity squared. This will give us our variance. So if we take the square root of that, we'll get our standard deviation. So you have to compute the expectation of x squared. We already know what the expectation of x is. I'm running out of room here, so let's do the expectation of x squared over here. Expectation of x squared. That's the sum of x squareds times the probability of x, because they have the same probabilities. So 0 times 0.272 plus 1 times 0.575 plus 4 times 0.121 plus 9 times 0.027 plus 16 times 0.004 plus 25 times 0.001. So finding the expectation of x squared. There we go. So we're going to put this all into our calculator. So again, 0 doesn't matter. 1 times 0.575 plus 4 times 0.121 plus 9 times 0.027 plus 16 times 0.004 plus 25 times 0.001. All right, so expectation of x squared is 1.391. So now we put that together down here to get our standard deviation. That's going to be the square root of this number, the expectation of x squared, minus the expectation of x, which is the mean, squared. And then we take the square root of that. So square root of 1.391 minus 0.919 squared. And we get a standard deviation of 0.7392. So 0.74 for our purposes. So 0.74. Okay, so that's one way to compute the standard deviation. You can do it the other way if you like. It's up to you, but this is the way I prefer to do it when I have a probability distribution. Okay, so now with this probability distribution, they ask us to compute a couple of probabilities. The first probability is, what's the probability that our random variable x equals 2? Okay, it equals 2, an exact probability. Well, that's easy. That's exactly what is in the probability distribution. So what's the probability that x equals 2? It's 0.121. Straight from the table. Okay. Now, they want us to compute the probability that x is at least 2. We have a couple different ways of doing this, but the most clever way to do it is use the complement rule. And that would be the same as 1 minus the probability that x is less than or equal to 1. So that's equal to 1 minus the probability that x is equal to, and here I'm going to put parentheses, 0 and 1, because those are all the ways that we can be less than or equal to 1. So that's 1 minus quantity. Now we reading from the table, the probability of 0 is 0.272. Probability of 1 is 0.575. 272 plus 575. It's important to have this in parentheses before you subtract it. Put it in the calculator. 1 minus parentheses 0.272 plus 0.575 gives us a remainder of 153. So I've got a lot less space here. I'll just do a point. So this is equal to 0.153. So that's one way to do this. Honestly, whenever you have an at least probability, it's usually the best way. Not always, but often is the best way. So this was a simpler computation than it would have been. We could have done it directly by finding the probability of 2 plus probability of 3 plus probability of 4 plus probability of 5. And we have all those numbers and we can add them all up. It's really not that much more work, but this is just more clever. We only have to use 2 of the numbers instead of 5 of the numbers or 4 of the numbers. All right, 6.1. So that's I felt like that one really captured everything we needed from 6.1. Now let's look at 6.2. 6.2, we're dealing with the binomial probability distribution. This is maybe the hardest section on the exam, depending on I guess it's depending on who you are and how you feel about some of this stuff. So you definitely want to read over this chapter and understand what a binomial experiment is, and just familiarize yourselves with the formulas and the definitions in this section, because this is maybe the most information-laden section. So what I wanted to do is just show you how to compute the probabilities again using the calculator, since this definitely helps you shortcut this process. So we're in section 6.2, binomial probability distribution. The first 3 problems here, they give us the parameters and ask us to compute the probabilities. So in number 22, they tell us that the sample size is 20, the probability of success is 0.6, and we're interested in the probability that x is equal to 7. So probability that x is equal to 7, that's big X. Well, using the calculator, we would use the binom PDF, because we have an equal sign here. We use the PDF, and remember what the inputs are here. It's NPX. So NPX. So that's exactly what we'd use to compute this. So to get there, we hit the second button, we hit the vars button, we scroll way down till we get to the binom PDF, CDF. You see both of those. We choose the PDF function. We put in the inputs 20.617, 20, 0.6, 17. Boom. And we get a number. This is the probability, 0.01235. 0.01235. Okay, carrying on. Now we have different parameters. We're asked to compute the probability that x is less than or equal to 3. So when we have a less than or equals to, we use the binom CDF function. which only computes less than or equal to's. Okay, so this binom CDF computes less than or equal to's. It has the inputs NPX again. And you put in the X for the up to, it's less than or equal to 3. So that's the X that we put in. So we're using the binom CDF. We'll get to it the same way. Second, vars, scroll way down till we get the binom CDF. Then we put in the inputs that we have up here, 9, 0.2, 3. And we get 0.914. Okay. Finally, in this third problem, we're asked to find the probability that X is greater than or equal to 12, or the other way to say this is at least 12. As soon as you think at least, you should think, especially to use your calculator, you have to rephrase this probability in terms of a less than or equals to in order to use the binom CDF. We cannot use the binom CDF directly for a greater than or equal to. So we use the complement rule because this is an at least probability, and we translate it into the probability 1 minus probability that X is less than or equal to not 12, but 11, because that is the complement to greater than or equal to 12. So 12 is included in this probability, so its complement should not include 12. Once you have a less than or equals to, you can use the binom CDF to compute that probability. So I'll put it down here. That'll be 1 minus binom CDF with the parameters N, P, and X, which will be 11 in this case. Second, vars, scroll down, binom CDF, N is 20, P is 0.7, X is 11. So that's 0.11, blah, 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 blah. Now be careful, this isn't our answer. Remember that we're doing this in the context of a bigger problem. So it's 1 minus this result. So 1 minus second answer. That answer brings up the previous result. So this is the answer they're looking for. 0.886, and I'll stop at 7. 8867. Yeah. So be very careful about using the calculator to do these problems. The binom CDF in particular has limitations. You can only use it to compute probabilities with a less than or equals to. If it's a greater than or equals to, you can use the complement rule to translate it, but be careful that you decrease the X by 1. Okay. So one last example from 6.2, number 43 here. We're told that flights from Dallas to Chicago are on time 80% of the time. Let's take a sample of 100 flights. And first, we want to compute the mean and standard deviation for the distribution. So this is definitely a binomial distribution. Either you're on time or you're not, and we have a fixed sample rate, and each flight is independent of every other flight. They shouldn't affect each other usually. So we can use the formulas that we know. The mean for a binomial distribution is N times P. N is 100 here, and P is 0.8. So that should be 80. Okay, so that's your mean. Standard deviation, remember, is the square root of NPQ, where Q is 1 minus P. So that's going to be the square root of 100 times 0.8 times 0.2. Sorry. All right, so that's our standard deviation. Square root of 100 times 0.8 times 0.2. And that gives us a standard deviation of 4. So mean of 80, standard deviation of 4. So a mean of 80 means on average 80 out of 100 flights are on time, which is what we expect. Excuse me. So here's the question: is it unusual to have 75 out of 100 flights on time? Is it unusual? Well, there's various ways to compute this. One way that I can immediately see is that, okay, generally speaking, we say that an event is unusual if its probability is outside of, or I mean, if the value that we're interested in, we say a value is unusual if that value falls outside of 2 standard deviations of the mean. So with a mean of 80 and a standard deviation of 4, 2 standard deviations down from 80 would be 72. And 2 standard deviations up would be 88. So as long as the value falls between 72 and 88, it's not unusual. And 75 falls within that range. So it's not unusual. Not unusual. The other way to do this is to compute the probability directly. This is a binomial distribution. So we say second vars binom CDF. And here we would have an n of 100, a p of 0.8, and here we would be counting up to 75. So this probability is 0.13, which is in excess of 0.05. It's greater than 5%. So as long as you're greater than 5%, you're not unusual. So the answer is no. A couple different ways of seeing that problem. Are we within 2 standard deviations, or is the probability less than 5%, or is the probability greater than 5%? If either of those things are true, then you are not unusual. The value is not unusual. All right. Okay, so last little section here for our review. I chose some straightforward problems from 7.2. 7.1 is laying out all the basic theory of the normal distribution. That's a lot of info that you need to just study. And me reviewing it is just me going over the lecture again. So watch the lecture, read the book, go to tutors, whatever you have to do. I namely wanted to go over this selection of problems just to show you how to use the calculator to compute these probabilities. So we know that, I should say X, the idea here is X is normally distributed with a mean of 50 and a standard deviation of 7. So with that in mind, we're going to compute all these probabilities. All right. Probability that X is greater than 35. So I've shown you how to do these with calculators. Here you're going to use the normal CDF. And remember, the inputs for the normal CDF are lower bound, upper bound, mean, standard deviation. So lower bound here is 35. Upper bound is something very large enough. I usually put E10. Mean is 50. Standard deviation is 7. So this is what we're putting into the calculator. Second vars, normal CDF is the second one down. 35, E10, 50, 7. Boom. And we get a result of 0.984. All right. Now we want to compute the probability that x is less than or equal to 58. So again, we use the normal CDF. Lower bound, something sufficiently negative, negative E10. Upper bound is 58, mean is 50, standard deviation is 7. So that's what we're punching into the calculator. I'll just go over it again. Second vars, second option, negative E10, 58, 57. And we get a result of 0.873. All right, number 30. We're calculating the probability that this random variable will be between 40 and 49. So yet again, normal CDF. Lower bound 40, upper bound 49, mean 50, standard deviation 7. There is a trick, by the way, if you're doing lots of these problems with your calculator. Rather than access the function every time, you can simply hit second and then enter, and it brings up the last thing that you input, but now you can edit it. So I don't have to go find the function again. I can just change the inputs. Sometimes this is more trouble than it's worth, because you have to delete some things if you have it, yeah. But sometimes it makes it easier. Oh, crap. So normal CDF, lower bound 40, upper bound 49, mean 50, standard deviation 7. Hit enter, and we get an answer of 0.367. All right, so that really covers all the ways that you can use the normal CDF function to compute probabilities. Now, these last two problems, you're asked to find the 90th percentile and the 38th percentile. So for these problems, you're not, let me draw a picture here for number 34. You've got your bell curve, and it's asking us for the 90th percentile. So there's a value down here on the x-axis, which we call P90, that we're looking for. And that P90 is the x value that corresponds to the area, the lower left area of 90%. So that's what we're looking for, this P90, the value on the x-axis. We're not looking for the area. So all these other probability, that when we're computing probabilities, we're finding the area. Here we have the area, we don't have the value. So in this case, we use the inverse norm function, which takes in 3 inputs. The first is the area, then the mean, then the standard deviation. So inverse norm, access it the same way. Second vars, inverse norm is the third selection down. Bring it up, feed it the inputs, 0.90, 50, 7, and it gives us a result of 58.97. So what that number is the number on the x-axis that if we computed the area up to that number, we'd get 90% of the area. Okay, so one more time for good measure, what's the 38th percentile? P38. That's going to be inverse norm. And here we'll put 0.38 for our area, same mean and standard deviation. Second vars, third selection down, 0.38, comma 50, comma 7. And we get a result of 47.86. Okay, so there's obviously a lot more to these sections. There are word problems where you need to be able to translate the information given into the proper information so that you can use the calculator and these functions to compute the probabilities and so forth. That sort of thing you just have to practice. There's no amount of me going over all those problems that's ever going to make it click for you. You have to do it so that you can understand the language that you need to look out for and how to translate it. Once you've translated it, then everything's as simple as I've shown you here using the calculator. You have to go through the word problems, identify the mean and the standard deviation and whatever other information they've provided and use it accordingly. Okay. So that ends the review section for the exam on Thursday. Don't forget, I did do a problem session last week for 8.1 and 8.2, which will also be on the exam. So that problem session should suffice as a review for those sections. Study, study, study. You know the parameters of the exam. It'll open up on Thursday morning, and you will have until Friday morning to complete it. So 24 hours, 3 attempts, and it will be timed. I will give you ample time to complete it. So don't worry about the timing. Just worry about studying and making a good grade. All right, y'all. Good luck.